Александр Борисович сейчас опаздывает, а Павел просто не придет сегодня. Хорошо. Okay, so now it's another lecture about Fedosov's quantization. I hope today I'll conclude this topic, at least the classical, classical part of Fedosov quantization. So last time I spent lots of time. So last week I spent lots of time trying to constructing the space of sections of certain infinite dimensional algebra. I remember, as far as I can remember, I use this notation for it. So this is the space of all. This is the total space of the fiber bundle over the base space M. Omega is the symplectic form. So the fiber of this is the completed Weyl algebra over R to N with respect to, well, actually you can always assume that the symplectic form at the fiber is standard, but actually it depends on the fiber. It actually depends on the point X in M. So we have this fiber bundle, and we have denoted. So I'm not going to discuss the completion. I'm just going to write down the generic, the formula for the generic section of this fiber of this fiber bundle. So the generic section has the form A equal to the sum over K and multi-indices I, H bar to the power K, and now multiplied by certain coefficient, function coefficient, depending on index K and I. It depends on the coordinates in the base. And also we have the coordinates in the fiber in power Y. Here the sum is taken over all K greater or equal to certain negative integer n, minus n, and all multi-indices I with only one condition, that the sum of K times 2 plus I goes to infinity. In other words, there is only a finite number of terms of any given weight here. Okay? So, is there anybody else going to enter this translation? So, in case there is, please let them enter, and also warn them by chat that they should watch me via YouTube and ask questions via Zoom, because I don't have hand-free headphones with me right now. So yeah. Okay. They need to. Yeah. So they need to watch. There is no sound on Zoom right now because I switched off my microphone. Yeah. And if they want to ask a question and listen to me, they should go to YouTube. So they should listen to me at YouTube and then ask questions using Zoom via you. Okay. Okay, so here we have this fiber bundle. We are going to consider the space of sections W hat H of M is the space of sections, of smooth sections, of W hat C H M omega. And then we discussed the notion of symplectic connection. So symplectic connection is any linear connection on the manifold which is symmetric linear connection on Tm, and also verifies the condition that nabla of omega is equal to 0. For any symplectic connection, we can consider its extension to the Weil algebra fiber bundle, Weil algebra bundle. That is to say, that is W hat H bar C M comma omega. And so it gives you a well-defined map which verifies the Leibniz rule. In this case, nabla x of A times B is equal to nabla x A times B plus A times nabla x B. Here, the asterisk denotes the pointwise product in Weil algebra. Right? And X is any vector field. In M. What is also important is that we can actually modify slightly the notion of our bundle so as to consider differential forms on M with coefficients in this, with values in this fiber bundle. I explained this last time. So denote these forms by W hat 1 H M. So these are differential one forms on M with coefficients in sections of this Weil bundle. Then nabla can be regarded as a map from W hat H bar of M into W hat H bar 1 of M. Then we can extend this further to covariant derivation nabla from W hat H bar K of M into W hat H bar K plus 1 of M for all K from 0. So here we can assume, well, that is equal to W hat 0 H bar M, right? All the way up to K equal to 2n. 2n is a dimension of M. Right? So we can extend this covariant derivation to this set of maps which gives us a kind of complex, chain complex or cochain complex. W hat 0 h bar. I will omit m from my notation from now on, often to W hat 1 h bar, to W hat 2 h bar, and so on. So nabla is this map until we get into W hat 2n h bar of m. Of course, there is nothing, we cannot go further because there are no differential forms of higher degree than 2n on our manifold. But which is worse than that, or probably better than that, it is that nabla square is not equal to 0 here. So this is not actually complex. It is just a chain of maps. Our purpose is to modify nabla further. So you remember when we constructed our symplectic connection, we took any connection, any linear connection, symmetric connection on our manifold, and then added some correction term to this connection so that the resulting connection verify the condition we need, right? So now we shall further modify our symplectic connection so as to obtain nabla square equal to 0. Why this is possible? It is that actually, oh, sorry, this is worse. Just. Oh. So again, naively speaking, it is not always possible to find a connection which verifies this flatness condition here, because not every manifold is flat. However, as I explained, the nabla square operator from wk h bar to wk h bar plus 2, so k plus 2 h bar, has a very nice form which you can actually check. Nabla square of A is equal to the graded commutator of A with certain element omega of y, which is an element which is a global section, well, omega of y is a global section of this connection, of this fiber bundle. This globally defined differential 2 form on M with coefficients in Weil bundle. Namely, what you do, you just consider the usual connection form, usual curvature form of our connection. Curvature is a differential 2 form with coefficients in the endomorphism of the fiber of our original connection, which is just the tangent bundle of our manifold. So this curvature has the form Fij, PQ, right? dxp wedge dxq. So xp and xq are local coordinates, and ij are coordinates in the fiber. So they're different. Then we use the symplectic form to lower down the first index. And then we multiply it by yi and yj. So yi and yj are coordinates in the fiber of our fiber bundle. And one can check that this is globally defined and that this formula actually holds. So I'm not going to prove this right now, but it's a good exercise to check it. Actually, you can just check that. It is just enough to check this on generators of our fiber bundle, since both this formula and the left-hand side of so the right-hand side and the left-hand side of this formula both didn't define derivations of the Weyl bundle, of the Weyl algebra, right? So every derivation is uniquely determined by its values on generators of the Weyl algebra. So it's enough to check this formula on generators of the Weyl algebra. So you just think that A is equal to Y, right? And then check this formula, and this is straightforward. So as you see, the right-hand side, the action of the curvature is for the curvature operator is given by a commutator in Weyl algebra, and it is our luck that Weyl algebra has a rather large non-trivial center. So the idea is look for a modification of nabla, so that first this modification, let's denote it by d, so that d still verifies the Leibniz rule with respect to the star product. So here I use the graded Leibniz rule because now I allow A and B to be differential forms with coefficients in Weyl algebra rather than just sections of Weyl algebra. And second, d square is equal to the commutator of d square of A is equal to the commutator of A with an element omega sub d, where omega sub d is an element in the center of this algebra. Now the center on the right-hand side is easily understood because the center of any Weyl algebra consists just of the coefficients ring. Yeah? Just usual Weyl algebra has a very small center. So every fiber of our fiber bundle, the center is just given by the scalars. But these scalars now may depend on the choice of the point in the base, in M. So we conclude that the center of this, well, generally speaking, of any differential form in M with coefficients in Weyl algebra is just the differential form, usual differential form in M, but probably it can depend on H bar. So as far as H bar minus first is concerned, there can only be a finite number of terms with negative degrees in H bar, and the coefficients with positive degrees in H bar, there can be infinitely many of them, right? So now here we need to put star equal to 2 here. And the question is, how in the world are we going to find this modification which would verify this condition? Now this can be done pretty well. It's not easily, then at least naturally. So there is, roughly speaking, a unique choice of this modification which can give us the desired result. And it is our purpose to show that this is actually possible to achieve. But first we need to explain what kind of choice we need. So first, we need to preserve this property in our modification. So whatever modification this be, it should not disrespect the Leibniz rule. So this modification can only be by adding. So you know that nabla verifies Leibniz rule. A modification is given by adding certain differential operator, certain term to this nabla in such a way that Leibniz rule is preserved. Now, while algebra, as I explained, has very poor store of derivations. Actually, every derivation of while algebra is inner. That is to say, it is given by a commutator with a certain element. So we should find certain correction term, certain element with which we shall commute. And that is the only way to preserve this Leibniz rule. Because every other operator, there is no other ways to preserve Leibniz rule except for this one. Well, actually, if nabla is given by the Ram differential plus gamma ijk, then we can again consider gamma ijk equal to omega I p gamma p I jk, right? And then we can, so this will be, I forgot to say that we actually need dxj, right? So here we have dxk. So this is actually differential one form, locally defined differential one form. If you freeze these two elements, these two indices, then what remains is a locally defined differential one form. If you unfreeze them, then you get a locally defined differential one form with coefficients in matrices. So I do the same trick. I lower the index of this matrix, I get this kind of element, right? And then what else do I do? Let me see. Let me see. I didn't forget something. Just, I want to show that actually nabla can be written in the form differential, the Ram differential plus the commutator of A with certain element gamma y, right? So I just want to remember, I don't remember the exact formula for gamma y, so I need to check it up in my notes. Just a moment. So where is it? Actually, yeah, here it is. Yeah. And now I need to, so yeah, gamma y, I forgot if there is some coefficient I need. Yeah, but there is actually. The coefficient should be square root of -1 times divided by 2h bar. And then I take gamma I j k times y I yj. Right. And times dxk. Right. Yeah, okay. Now this formula is correct. So as you see, even in the usual case, we still have the same form. Any derivation, any covariant derivation, any covariant derivative on our vector bundle has the form of the RAM differential plus certain commutator. The problem is that here gamma is only locally defined, and I am looking for some globally defined delta gamma in omega hat 1, so w hat 1 h bar of m. Okay. So now this is the only way I can do this to preserve the Leibniz rule. Now the question is if it is possible to find delta gamma in such a way So let us denote this correction by d. That d square is given by a commutator of certain element that's denoted by, okay, phi twiddle with a. And we also assume that phi twiddle is some element in omega 2 of m with this h bar minus first h bar space, right? So that's what I'm going to do. And the answer is given by Fedosov theorem, which I formulated last time. And the answer is positive. But before we proceed, I'm also going to show that this theorem is actually the best thing we can get. We cannot actually improve this theorem anyhow without losing generality. I mean that the actually it is easy to show that the RAM differential of phi bar, of phi twiddle, is equal to 0. Indeed, phi twiddle is here, so it is in particular inside w hat 2 h bar of m, right? So d of phi twiddle is equal to d, let us say, yeah. So according to the well-known Bianchi identity, the covariant derivation of the curvature vanishes. I'm not going to prove this. This is just Bianchi identity, right? On the other hand, d of phi twiddle is equal to the RAM differential of phi, just because of this formula. Oh, yeah, I also forgot to say that. I also erased this. I even said it, but I forgot, but I erased this. Nabla itself is equal to the commutator plus the RAM differential. Right? So all commutators which we have actually disappear because phi is in the center, as we assumed. The only thing which remains is d phi. So we see that it should be equal to 0. So whatever we do, the only thing we can do is actually, we should take a closed differential form. And this is precisely what Fedosov does. Only another assumption, which is actually quite important for the construction, without it the construction would become quite hard to follow, is the assumption that we choose this phi in a very special form. Namely, take phi twiddle as omega divided by, I think it is just omega. Probably divided by h bar. I don't remember this. I need to check this again. It's important to keep all the coefficients correct. So, okay. Philosoph theorem, it says that, yes, I forgot to say that it should be minus square root of minus 1 divided by h bar. I always forget these coefficients. And the first term will be equal to omega. So omega is just a symplectic form. As you know, symplectic form is closed. So we make no mistake by taking it. There is no objection to this. And the rest is just phi. And it turns out that phi is differential two form with coefficients in h bar. And it turns out that phi can be arbitrary closed form. That's the result. Okay, so Fedosov theorem says that, so let me again restate it. Theorem. For any phi, there exists a differential, an abelian connection D on W hat star h bar of M such that D square of A is equal to the commutator of minus omega divided by h bar. Also this square root of minus 1, probably minus can go here, plus phi with A, which is 0. Okay, I'm going to prove this now. So this take an explicit term given by the fixed symplectic form is actually an important step in the proof. This gives us actually the nice way to find the correction term delta gamma. Actually, we take the following expression to be delta gamma. So delta gamma should be equal to, again, I'm forgetting the terms, so the coefficients which should stand there, and I need to pick it up. Okay. So what I do, I take the first term of the form square root of minus 1 divided by h bar omega ij yi dxj. So the summation of repeating indices is understood, right? And this is a globally defined differential form in our space, in the space of differential bond forms with coefficients in Weil algebra. So, but this is not all. We also need to add certain new correction term, zeta. What we have done, I've just took explicit parameter, explicit first part in our correction term delta gamma, and I put it to be in this form. That's the only thing which I assumed. Now I'm looking for zeta such that this connection would hold. So taking everything into account, what connection do I have now? So nabla of A should be equal to, sorry, not nabla, d of A. D of A should be equal to nabla of A plus the commutator. Let's denote this by omega y. Omega y with A and zeta with A. Right? Now this operator is very important and is easily seen, is easily described. Namely, first of all, this operator, let's denote it by delta of A. The first property is that this operator is actually a derivation. Why? Because every commutator is actually a derivation, as I explained. Now, it is enough to check the value of this derivation at any generator of our Weil algebra. So let us take, for instance, A equal to y. Okay, so what do we do? I'll probably, okay. Delta of, let me see. Delta of what I'm going to take? I'm going to take delta of, okay, y. Yj, probably, p. What is it equal to? It is equal to, well, again, up to the sign. I'm sorry, I think there was sign minus here, but we shall restore the sign pretty quickly, pretty soon. So what we have is square root of minus 1 divided by h bar times omega ij times dxj. You see, there is no other gradient here, so we can just take dxy from under the commutator without any problem. And here we have the commutator of y I with yp. And now this is equal to yi and yp. So what is it equal to? It is equal to pi ip times square root of minus 1, sorry, times h bar divided by square root of minus 1, right? So what we have here is, so these two factors will cancel out. We shall just have omega ij times pi, sorry, omega ij here, pi I p d x j, right? Okay, great. So what does it mean? It means the following thing. We first, these two tensors are inverse to each other. The only problem is that here we take summation over the first index, not over the second index, right? So what we get, it is not delta jp, it is minus delta jp. So in the end, we shall have minus dxp here, right? Okay. Now I'm afraid I have made a mistake with the sign. Let me check it again. The sign is important here. I really want to keep it straight as much as I can. Okay. Right. The only problem is that I would prefer to put minus delta here rather than delta, just to restore the sign in its proper place. Now, so it means that delta of A can be written in general as the application of the operator dxp d over dyp, roughly speaking, to A. So this is the rough way to write down this operator delta. What are other properties of the operator delta? For instance, what is delta square? What is delta square? It is just a double commutator, right? Omega y with omega y with A. Now, using the Jacobi identity, we see that up to the sign, I think it's 1/2, it is equal to 1/2. But yeah, plus or minus doesn't matter very much to me. It will show up later, but now I don't care about this. It is minus 1/2 or plus 1/2 of the commutator of y, omega y with omega y with A. Now, unlike the usual case, this commutator is gridded commutator. So it's actually omega y plus omega y, omega y. So it doesn't vanish identically, right? But what we have instead, it is delta of omega y. If you look at omega y, so here it is more or less, right? It is d over dyp times dxp, right? So it is equal to minus square root of minus 1 divided by h bar omega. Right? Or plus. Okay, I don't care about this. I think it's plus. And this is a central. So in any case, this vanishes. But for the different reason. Not because this is equal to 0, but because it is central. Right? So taking this into consideration, what term do we have when we square our operator? So what do we do? D square applied to A. What shall we get? We shall get nabla square applied to A, right? Plus yeah, delta square applied to A plus zeta, comma A plus mixed terms, right? So what mixed terms there will be? Nabla of omega y commuted with A, right? And also delta zeta, or minus delta zeta, commuted with A. And finally there will be, will there be anything else? Oh yeah, there will be nabla zeta applied to A. Right? So, taking into consideration that this is equal to the commutator of omega y with A, we see that the curvature which we're looking for has the form phi tilde. Should have the form. Let me write it down from my notes. How does it look like? It looks like omega y, sorry for bad handwriting, plus nabla omega y, nabla small omega y, minus square root of minus 1 divided by h bar omega. It is here where I really need this explicit formula for this. And it is here where the sign actually shows up. I'm sorry I actually forgot about the sign, but please, yeah, if you need it, ask me. I'll restore it. Then I also have minus delta zeta. Again the sign, but here it's correct. And finally, plus 1/2 of zeta commuted with zeta. Now I assume that phi tilde has the form minus square root of minus 1 divided by h bar omega plus phi, where phi is again closed. So this thing cancels out with this thing. Very nice. But now I still have a very huge equation which cannot be solved directly. At least it is not evident how to solve it. Omega phi is equal to this sum, this plus this minus this and plus this. So what I do next? I take delta operator to the left, and this is here where I actually take use of this phi, of the sign. And I get finally the equation of the form delta zeta is equal to omega y minus phi plus nabla of omega y, small omega y. This doesn't depend on zeta, so I shall denote it by, say, omega, I don't know, something, I don't know, probably omega 0, I don't know. Something like that. Okay? So we shall. It's better to put it. Well, too many elements or too little letters. So I don't know what kind of letter to use here. Maybe. Well, let's put it zeta tilde. Zeta 0. Okay. Zeta 0 tilde. Let's do it for a while like this. Okay? Plus there will be something dependent on tilde. And this something is easy. I think I forgot to say nabla zeta. Nabla zeta here, right? Yeah. Did I miss it here? Yes, it is here, but I just forgot to write it down. Yeah. Yeah. Plus nabla zeta. And plus 1/2 of zeta zeta. So we have this operator, and well, shortly speaking, we have delta zeta equal to zeta tilde 0 plus nabla zeta plus 1/2 zeta zeta. And we are going to solve this equation, but how? To this end, and this is actually a pure genius, I would say, because the idea is really remarkably simple and has a very, well, deep roots in analysis and in algebra. The idea is to consider the dual operator of delta. The operator delta, as I have already explained, can be written down by in a short notation as the sum over p of dxp times d over dy p. So that's a kind of de Rham operator. As you probably know, for any de Rham operator, one can choose its dual, well, Hodge dual. Here, it is natural to say that its dual will look like d over dxp times yp. The problem is that this here operator should be, well, it is easy to define the differentiation of Grassmann algebra. Grassmann variables are almost as good as usual commutative variables, right? But multiplying by yp is a little bit tricky. The problem is that if you just take multiplication from the left, then delta star square will not vanish if you do it improperly. So what do we do? Let me recall you that I have an identification of W, the Euler algebra, W hat H bar, with S hat H bar. So this is linear identification. So here I take a kind of fiber bundle of algebras, but now I have only symmetric algebras. They have commutative multiplication. This multiplication does not match the multiplication in Weyl algebra at all, but we have a linear isomorphism of the right-hand side and the left-hand side. So what I do, I transfer multiplication by yp from right to left using this linear identification. And I use the sign yp circle to denote this multiplication. Now, since the multiplication of y by yp is commutative on the right-hand side, the multiplication with circle by yp and yq commutes. And hence, delta star square is equal to 0. Again, this derivation is graded. So when you differentiate first by dxp and then by dxq, you obtain minus sign. But this multiplication is commutative. So when you have two terms, one coming from first differentiation by dxp and then by dxq, and then a term which comes from a differentiation first by dxq and then by dxp, these two terms will come with opposite signs, but these two terms are equal. So they cancel out just like the terms in usual de Rham derivation. So delta star square equals to 0, is equal to 0. Delta star square is to 0, but it is not enough. The key to the Hodge theory, as you have probably, well, studied it, is to consider the Laplace operator. A kind of Laplace operator here is the sum delta delta star plus delta star delta. Okay, is it good to leave it as an exercise? It's a good exercise to check, now that you know everything, that this operator applied to A will be equal to P plus Q times A, where A is an element in W hat Q h bar of M. So Q is just the degree in direction of the ramp forms. And P is a degree which comes from this identification. You see, S hat is graded algebra. And we can use this linear isomorphism to transfer gradient from right to left. So in particular, this operator is invertible almost everywhere. You see? It is almost everywhere invertible. Let's denote it by delta. Okay. What is it? What's this? I'm sorry. It seems that I okay. Oh, I'm sorry. I think I lost my I lost these notes I have. I'm sorry. It needs some time to find the okay. No. Sorry, I need to find this. Oh, it's really bad. Problem is that there is a few other places where I really need to take care of the signs and everything, and this actually takes some time. So just to make sure, I'm sorry for a short break. Okay. If you have questions, you can ask them meanwhile. Okay, here it is. So these are my lecture notes. Just try to, yeah, here it is. Okay, so eventually we denote delta minus first of A. So let A, so now we extract homogeneous components from A, and we denote by A p sub pq the homogeneous component of degree p and q with respect to these two gradings. And we denote, and then we set delta minus first of A pq equal to 1 over p plus q times A if p plus q is not 0, and 0 otherwise. And then we had the following very nice formula. Which is actually the straightforward, the straightforward generalization of the what they call the green function in physics. Delta minus first plus delta minus first green projection formula, actually, is what we have. APQ is equal to A PQ if PQ not equal to 0. Right? And 0 otherwise. Right. It's again, it's a homogeneous component of A with respect both to Grassmannian and symmetric grading. So finally, we have the following decomposition, which is actually the key to the whole thing. For any A in Weyl algebra, graded Weyl algebra, have A is equal to delta minus first is delta minus first delta times A plus A 0. So this is the formula. Let's again look at our equation. I have this equation. Let us do just one assumption. Suppose delta minus first of psi of zeta is equal to 0. And also the lowest gradient of zeta is equal to 0. Then what we can do, we can apply delta minus first to this equation. What we get? On the left, we have delta minus first delta applied to zeta, which is equal to delta minus first delta plus delta minus first applied to zeta, because the second term cancels. Now, this is equal, according to this decomposition, it is just equal to A, because this term also vanishes by our assumption. So this is the assumption, the additional condition on zeta that we make. We are looking for zeta which verifies this condition and this equation. Right? That's what we do. In this case, we have this equality. Right? This is just equal to zeta. That's on the left. Then on the right, what we have on the right, we have delta minus first zeta tilde, we denote it by zeta 0, plus delta minus first of nabla zeta plus 1/2 of commutator zeta and zeta. And that's the final equation we're going to solve.
Why the left equality is true? Why is the left equality is true?
Which one?
Left A is left on the left hand side of the black ball.
This one?
Yes.
Well, it's just because this one.
Yeah.
Well, this is just the consequence of our definitions.
No, I mean for PQ it's okay, but if P is equal to Q, why there should be?
What? But this is plus. We have P plus Q. The only place where this fails is when P and Q are both 0.
Okay. Or P is equal to minus Q.
You cannot do this.
Positive,
Yeah.
Positive.
It's always they're always positive. There is no problem with this. Yeah.
But is there really always positive? I thought that.
No. These are always positive because P is just the Grassmannian gradient. It is always non-negative.
You mean the degrees of xi?
There are degrees of dxi. Yeah, the
And
number
what is the degree of
y's. Yeah, number of y's. Oh, sorry, someone is calling. Okay, let's go on. So we have this equation. And now we're going to solve it. We're looking for zeta, which verifies this condition, these two conditions, and this equation. And here is the way we solve this equation. We use iterations. So let's take zeta 0. Zeta 0 is given by this formula. There is no ambiguity here, right? We have omega. So zeta tilde doesn't depend on zeta at all. Zeta tilde only depended on the symplectic connection, on symplectic form, and on our choice of phi, right? Nothing else. So we have zeta 0, which doesn't depend on anything. And then we put zeta 1 equal to zeta 0. Oh, sorry. Let me check this. Yeah. Zeta 0 plus delta minus first of nabla zeta 0 is 1/2 of zeta 0, zeta 0. Then we do the same thing here. Zeta 2 is equal to zeta 0 plus delta minus 1 of nabla zeta 1 plus 1/2 zeta 1, zeta 1. And so on. So at nth stage we shall have zeta n plus 1 equal to zeta 0 plus delta minus first nabla zeta 1, zeta n plus 1/2 zeta n, zeta n. Yeah, we have this process. Why does this process converge? That's the first question. This is the iterative process, very natural process actually. But why does it converge to something? And that's not hard to say, because we just need to consider the difference of zeta n and zeta n minus 1. Zeta, or probably better to say zeta n plus 1 minus zeta n. What do we have? On the right we have two expressions of this sort. Zeta 0 cancels out when we subtract the first of them from the second of them, right? And then we have delta minus first of nabla applied to what? Zeta n minus zeta n minus 1, right? Plus 1/2 zeta n minus 1/2 zeta n minus 1 zeta n minus 1. And now this difference can be expressed as zeta n minus zeta n minus 1 commutated with zeta n plus zeta n minus 1. Just open all the brackets. What we have, so the first term will look like this. The last term will look like this with minus sign. But in the middle we shall have zeta n commutated with zeta n minus 1 minus zeta n minus 1 commutated with zeta n. Since zeta, both zetas, have degree 1 in Grassmannian direction as differential forms, these commutators coincide and these two terms cancel. Right? So I erase this and replace this expression by this. One half zeta n minus zeta n minus 1, zeta n plus zeta n plus minus 1. Now, what does delta operator do? Let me recall the delta minus first operator. It is just up to some renormalizational factor. Delta minus first is just delta star, right? Times some coefficient, right? And delta star it is d over dx p yp, right? You see this, so sorry, d over dxp, d dxp, sorry, I forgot about the second d. Okay, so what happens now? You remember that W hat was completion with respect to the total gradient. Completion right? So this operator increases gradient by 1 at least, because the multiplication by yp increases this gradient by 1, and differentiation by dxp does not change the gradient at all, does not change the gradient, you see? So this increases the gradient. The operator nabla does not change the gradient because it's just the differential operator. It does not influence y's, number of y's, right? It can only, if anything, it can only increase their number because we use this commutator with y's, right? So it increases, does not change. Same here. You see? If you take this element has positive gradient. So this total gradient again does not change or grows. Yeah? We see that the elements in parentheses have gradient greater or equal to the gradient of zeta n minus zeta n minus 1. An application of delta minus 1 increases the gradient. So from the point of view of convergence, this element is smaller than the element on the right, than this element, right? Strictly smaller. It means that this difference tends to 0. Right? The gradient of this difference grows indefinitely when n goes to infinity. So it means that there exists limit of zeta n when it goes to infinity, such that zeta verifies this identity. Delta zeta is equal to zeta 0 plus delta minus first of zeta, sorry, nabla zeta, plus 1/2 zeta zeta. It is just the identity because on both sides n, zeta n and zeta n plus 1 tend to the same element, right? Okay, nice. So we conclude that there exists zeta which verifies this condition. Yeah, of course there are many things which I need to add. I only mentioned that the gradient grows indefinitely, but of course you need to work a little bit more to prove the existence of this limit, in fact. So yeah, I'll meet lots of details here. yeah, completeness and everything, but I only proved that the difference of zeta n and zeta n minus 1 goes to infinity. It doesn't mean that the limit actually exists, but you need to, well, it means actually, but it's due to the fact that our topology, the convergence of our elements, is given by a very simple rule. In general, you know, it is possible that the difference of two terms goes to 0 while there is no limit still. That's the problem, but here it is not the problem. Okay, so we have this limit, and it verifies this condition. Also, let us apply delta minus first to zeta. You know, delta minus first is just the square of delta star. So delta minus first is equal to 0. Delta minus first square is equal to 0. So we have that it is equal to delta minus first of zeta 0. Right? And then, am I not mistaken? No. Yeah. And then zeta 0, I just forgot to, what is zeta 0? Let me recall this. Zeta 0 is, zeta 0 is again delta minus first of something. So it's actually again equal to 0, right? Yeah. And also we need to check that zeta 0, 0 is equal to 0. That was the assumption which we made. Now, to see this, it is enough to observe that delta minus first increases the gradient. In particular, it's enough to see that actually it's enough to see that zeta 0 and everything, all zetas, zeta n, are in W1 head of M. So in particular, at least this gradient is non-zero. So in particular, this zeta 0, 0 is equal to 0. So both assumptions hold, and we see that we have solved our problem. It is now interesting to check. So we just solved this equation under these two assumptions. So we have found the solution of this equation under this, verifying these two assumptions. Now, it remains to show that if we take nabla plus, minus delta plus commutator with zeta equal to d, then d square is the commutator with minus square root of minus 1 divided by h times omega plus phi. You see, we have solved this equation with these two assumptions. But we still need to work to show that what we obtain actually verifies the condition we need. So what do we do then? It is not so easy as you can assume, unfortunately. Okay. So take the difference. So let's consider this d, and let us denote by omega zeta the actual curvature of this connection. Something like this. Right? And let's take the difference. omega zeta minus the thing we need. And denoted by A. And what are the properties of A? We need to show that A is equal to 0. That's what we need to show. And what are the properties of A? First, delta minus first of A. So if you expand this carefully, and you see that it is equal to okay, something like zeta so in some notation which is actually a little bit confusing. So what is omega 0? Yeah, so I need this, yeah, there is this, yeah, I use this notation there, right? It was something which didn't depend on zeta at all. It was omega y minus nabla omega y plus phi. What is this? Okay, we have this. Minus delta zeta plus nabla zeta plus 1/2 zeta zeta. So this is the difference. Okay? So this is the thing we have. Okay, nice. When we now by definition this is just equal to delta minus first of zeta tilde 0 was just zeta 0, right? So what we have is zeta 0 plus delta minus first of nabla zeta plus 1/2 zeta zeta plus delta minus first delta zeta. But now this element is equal just to zeta. For the same reason, because delta minus first of zeta is equal to 0, and there is no zeta 0, 0 here, right? And we also use that expansion. Okay, nice. So what we have is just, oh, sorry, the sign is different here. It's important. Okay. Yeah? Yeah, precisely. This is the sign, minus. So what we have here it is just zeta. And here is minus zeta, so we get 0. So we say that delta minus first of A is equal to 0. That's the first equation we get. Let me erase everything, all the rest. What next? Take d of A. d of A is d of omega z minus, okay, here I think we denoted this by, it's probably better to denote it by something just to save the time. Let's denote it by alpha, I don't know. So first, d of omega zeta is equal to 0 due to the Bianchi identity, right? And now d of alpha is equal to the ramp differential of alpha, because alpha is a differential form which is in the center. So all the commutators which appear in the definition of d vanish. So, but both omega and phi are closed, so this is 0. So we see that, that A verifies this condition and this condition. What we do now, we observe that d of A is just nabla of A minus delta of A by definition, plus commutator of zeta with A. And just putting everything to the left and to the right, we see that delta of zeta, delta of A, so this is 0. Delta of A now is equal to nabla of A plus zeta A, this commutator. Okay, now we're almost there. Now we use the decomposition. Delta minus first delta A plus delta minus first A, when we apply it to A, is equal to A00, 0, right? Oh, sorry, not equal. Plus is equal to A. Right? That's what we have. Now A00 is 0. It doesn't exist because they both differential two forms. Now this term, the first term, this term vanishes identically for this reason. And this term is equal to delta minus first delta of A. So delta of A is equal to this. Right? Now look here. I have this identity. Delta minus first increases the grading, as I explained. Increases by at least by 1. Nabla does not change. Does not change grading, or increase it. Either doesn't change it at all or increases it. The same here. It either doesn't change the grading or increases this grading. So we see that A is equal to something with higher grading. But this can only happen if A is equal to 0. So A is equal to 0. And we eventually have this, the Fedosov theorem. Okay, now I not only have to explain the very briefly, since I'm totally out of time, I need to explain how this operator is used to define the star product. So we consider the complex. Now it is complex. H bar with 0 H bar. So 1 H bar. D to W hat 2 H bar 2 and so on to W hat to N H bar of M. And let's consider this complex with the complex which we already have, which we didn't notice this. When I take W0 H bar, I can use the operator delta. It also increases the Grassmannian degree and also squares to 0. So we have another complex now here. This complex in the bottom is actually acyclic. Since we know that we have this operator delta minus first, which verifies this condition, it is easy to see, it is just a simple exercise in homological algebra, that the only cohomology of the complex in the bottom is concentrated in this degree, and it is equal to C infinity of M with this probably like this better. Okay? The only cohomology is concentrated here. On the other hand, I don't have time to prove this, but it is an easy exercise for those of you who are familiar, with so-called homotopy perturbation lemma. Homotopy perturbation lemma. Actually, the operator D is obtained from the operator, okay, plus or minus doesn't matter. D is equal to minus delta plus some correction. In this case, it is often possible to show that the cohomology here and here are actually isomorphic. There is a very well-defined map from one complex to another. I can even write down the formula for this map in a little bit informal way. Namely, there is a map Q Q, which is equal to 1 minus delta minus first d plus delta. It is the correction term, actually. This is d plus delta is the correction. It is just the remaining part of d, right? To the power minus 1. So, and q minus first is equal to 1 minus delta minus first d plus delta. So this map Q is a map from let me see from where to where. Q is a map from here to here. So we have an isomorphism Q. Isomorphism from lower to higher, which in particular it induces isomorphism in cohomology. It means that the cohomology of the top of the upper complex is also concentrated in degree 0. And here it is easily computed. The cohomology in degree 0 is just the space of flat sections. And this Q, in this way, it follows that Q is isomorphism, induces isomorphism from C infinity of M with H bar, right, extended by H bar, to the space of flat sections of our bundle. And that's precisely what I promised. The way you construct Q is either by these explicit formulas or by the same iterative process, very similar to what I have explained. You can just, actually, if you want, you can just take these formulas and check that everything, that the identity I promised holds. Right? The main problem is that we need convergence here. But this convergence is again provided by the fact that the degrees of the elements here increase indefinitely. Okay. So that's the way you define Fedosov quantization and Fedosov star product. It's very geometric. It's not easy. Before I say goodbye today, I need to make one more observation. An important question, which is related with the deformation problem, is to describe all possible classes of deformation. We shall say that two deformations are isomorphic. Two star products, star 1 and star 2, are isomorphic, are equivalent. if there exists formal power series of differential operators T1 plus H bar T1 plus H bar square T2 and so on, such that T of F star 1 T of G is equal to T F star 2 of G. So it is important to classify all possible equivalence classes of such operators, of such subproducts up to this relation. And it turns out that in case of Fedosov's quantization, everything is uniquely determined by the choice of cohomology class of phi. You remember that when we constructed this correction term zeta, we chose it in such a way that the curvature of our operator D is equal to this fixed term plus some closed form phi. So since closed form determines a class in cohomology, we can define the characteristic class of our star product as the cohomology class of phi of the corresponding Fedosov connection. So this cohomology class is in fact element in degree 2 de Rham cohomology of M extended by this formal parameter. Right? It's usually people omit H minus first here. It is natural to just remove it from our considerations. And another interesting result, also due to Fedosov, is the following theorem. Star 1 is equivalent to star 2 if and only if the class of phi 1 is equal to the class of phi 2. You see that if the cohomology of our space is non-trivial, then there exist infinitely many, actually, continuums. I think it's continuum, right? As many, well, uncountably many, not just infinitely, uncountably many different classes of star products. So we have a kind of modulus space of star products, even in this simple case. The way this is proved is actually quite, well, geometrically it's quite simple. There are lots of technicalities there, but geometrically just the following thing. You need to prove, first of all, you just observe that everything is determined by the star product. Sorry, everything is determined by the Fedosov connection, right? So you need to show that two Fedosov connections are isomorphic somehow. Now, so Fedosov connection is a flat connection. If you have a flat connection on a space M, then you extend it by multiplying M by, M should be curved, but I multiply it by a segment. It is possible to extend flat connection from M to the segment. Just like flat connection on M is determined by differential form phi, this extension is determined by a deformation along the segment of this form phi, right? But then, when you have a flat connection on the product M times the segment, you can consider the equation of parallel transport in direction of this segment. And that's precisely how you extend flat sections from here to here. And it turns out that you can find these extensions if and only if the class of connection here is is homologous to the class of connections here. So that's how you do this. It's not easy. Well, as far as the geometry behind this is concerned, it's pretty straightforward, but all technicalities there are quite elaborate. You need to use this iterative process of Fedosov several times just to prove that everything converges. And that's how you do this. Okay, now everything is done, and I say goodbye to the audience in YouTube. Okay.
And next time, will Pavel?
Yeah, the next time Pavel Saponov will talk. He didn't come here because of some problems at his institute, in his university. He has to work there, has to do some, well, administrative stuff there. But next time he promised to come. He promised to come next time. Okay. So I turned off my my broadcasting in Zoom. I turn off this again as well.
Так что ты ему все расскажешь по-русски? Нет, впрочем, они могли записи смотреть.
То есть начали по-английски,
Ну да, да. Не, я думаю, они будут проверяться просто на этой неделе они должны отправить.
Do you have this Mid-Autumn Festival in Japan? Or is it purely Chinese?
What kind of
Mid-Autumn, Mid-Fall Festival. I know in China it's a big holiday.
I don't think so.
No,
we don't have such festival in Japan.
No such festival in Japan, I see.
And I didn't know about the Chinese festival.
Oh, I see. Yeah, it's a big thing in China.
For what?
It's just some traditional holiday. They have a week, at least 1 week break in beginning of
But in 2019, that was a big holiday.
Yeah, it was a big holiday.
Dedicated to the assume on